Hello everyone, welcome back to ptet.chemistry channel. In this video, I will specifically talk about the electrophilic substitution mechanism. Okay, so this typically involve what we call the aromatic ring. Okay, so meaning to say is to do with reactions involving the benzene ring, okay, which is known to be aromatic. As a result of this aromaticity, which is a property you have learned in your physical chemistry part of benzene chemistry, you have learned that that's the reason why it's doing substitution instead of addition, because you want to go back to that aromaticity stabilizing property. Yeah. Anyway, the electrophilic there, it's quite straightforward. Think about your alkene chemistry, and you know that there is the one that's rich in electron. You can also imagine that in the cocoa structure of benzene, which you could represent like that, or of course you can represent it as being the totally delocalized electrons, as we would have known it from crystallography techniques, as well as from the enthalpy of the enthalpy change for hydrogenating all double bonds in the benzene. The result in this aromaticity character being supported by those observations, all right, that we saw from enthalpy change of hydrogenation of benzene, or from crystallography data of benzene molecule, which shows that all the carbon-carbon double bonds are actually equal in bond length and not showing characteristic of an alternating double single. Okay, however, when I draw my mechanism for electrophilic substitution, I always like to think about it in terms of the cocoa structure, because it's very easy to spot to actually detect where the double bond is, just like we would do for an alkene. It's easy enough to do the bookkeeping with a cocoa structure, but knowing that it's actually fully delocalized, you know that this is just like a snapshot in time where the double bond happens to be there and you react it as such, even though it's not really the case. But in most examination body, as far as I know, definitely the Cambridge International, you'll be alright drawing the mechanism using the cocoa structure, for as long as you know that the delocalized structure is actually the correct version of it. Okay, so I'm going to get started. We need to generate our electrophile. To generate the electrophiles for these electrophilic substitutions, we can talk about the generation of chlorine plus. And the way you do it is you will need a ClCl. You will need a source of Lewis acid. We call this Lewis acid catalyst. Okay, you will see it being a catalyst later on. Lewis acid, because it has got empty orbitals. If you know your VSEPR, you will know that this is a sp2 aluminium with 3 bond pair but 0 lone pair. So this is actually trigonoplanar. So what happened is the aluminium looks trigonoplanar, but it has an unhybridized, we call it unhybridized, because aluminium by right has a 3s and a 3p. So here is only sp2 hybridization, which give it 120 degree. So you still have an unhybridized 3p orbitals on the aluminium, which means empty orbitals. Guess what? Yeah, therefore you can have a dative covalent bond form in such a way that a chloride minus, Cl minus, can enter that. And because you're forming chloride minus, then you will get a chlorine plus as well. That is your electrophile. This is the balance equation to generate the Cl plus, and it's required in a mechanism. If you don't have this, how can you do the electrophilic substitution starting from this? So this must happen before you can do the electrophilic substitution with the benzene ring. Okay, I'm going to generate a few other electrophiles, some of which might be useful to you, some of which might not be because they are not in a syllabus or whatever, but the idea is similar. Generally, we use the FeBr3 as the Lewis acid catalyst. Again, the idea of Lewis acid is that it has an empty orbital to accept a pair of electrons. So the idea really is just you form a negative charge due to the dative covalent bond from the Cl minus or Br minus into the empty orbitals. It's a bit more complicated with iron, I guess, being a transition metal, but we are more interested in the generation of the electrophile. This next one is an important one. You want to generate the NO2 electrophile. how in the world do you generate the NO2 plus electrophile? The plus is not on the oxygen, it's on the nitrogen. Okay. If I show you the shape of the ion, you'll be surprised as well. Yes, it's that. Okay. So what actually happened is the nitrogen uses the other lone pair to form a dative bond to the oxygen. So what actually happens is you get a linear molecule, 180 degree, with 2 sigma bond, therefore 2 bond pair of electrons, 0 lone pair of electrons. The 2 bond pair repel equally. You get a linear geometry. By right, I should have drawn it like this, like that, okay? Where one of it is actually a dative covalent bond. One of it is actually a dative covalent bond, which then you can convert to dot and cross, but I'm not going to do it here. For the normal covalent bond, it will be 1 cross, 1 dot, but for this, it will be either 2 cross or 2 dot. It has to come from the nitrogen. That's the definition of dative covalent bond. You have learned this when you learn NH3 forming NH4+. So similar kind of concept, yeah? So here, we really need concentrated HNO3 and concentrated H2SO4. So quite an extreme mixture of 2 very concentrated acid, yeah? So the HNO3 react with the H2SO4. I can tell you the H2SO4 is the stronger acid. We know our end goal is to get NO2 plus, all right? I like to circle my plus charge, as you can see, because I'm short-sighted, so I tend to lose track of things easily. If I circle, I don't lose track of it. It's alright if you don't circle them, really. Okay, the H2SO4 is the stronger acid. It will donate the proton. It will donate the proton, and itself will become conjugate base. When the acid donates the proton, it loses the H+, it becomes conjugate base. Alright, this is in the idea of AS chemistry in the Cambridge International, where you are supposed to know acid-base theory, giving you the conjugate acid and conjugate base respectively. Sorry, not respectively, but it will give you the conjugate base after the acid donates the proton. The base, after accept a proton, it will give you the conjugate acid. Alright? It will also dissociate, of course, to give you the H3O+. That's how I know it's H3O+ and not H2O. And this equation will not be balanced unless you get it to be H3O+. Okay? So it kicks out H2O because H2SO4 concentrated is also a dehydrating agent. So it kicks out H2O from here eventually. Alright? So it kicks out H2O from it, but in the presence of an acid, the H2O will form a dative covalent bond and it will simply form the oxonium ion, which is H3O+. This thing, as you can see, I know I have one of these, and this is plus, and this is -1, so I need 2 of it to balance out the +2 charge. Okay, that's how I remember it usually. So now I have 2 HSO4, meaning to say I must have 2 H2SO4. Well, let's double check the equation. The 1N give you 1N, the NO3 give you the NO2, I have 1 extra oxygen. The 1 extra oxygen goes here, okay, because the O2 comes from here, the HSO4 comes from there, there are 2 of it, okay. The extra oxygen from there goes there. There's 1 extra hydrogen, it goes here. There's 4 hydrogen, but there's 2 hydrogen. So there's extra 2 hydrogen from here to here. The extra 2 hydrogen goes there, plus the extra hydrogen become 3 hydrogen. Okay, so the atoms are balanced, and you get your electrophile. That's the most important thing. All right. What are the other common electrophiles? This is the specific name of the reaction. It's called Friedel-Crafts alkylation. But all of them come under the big umbrella, which is the electrophilic substitution reaction, yeah? So when they ask what type of reaction, it has to be electrophilic substitution. I'm just telling you that there are different type of, there are different names for each specific reaction. You want to alkylate, so you want R+, you want a carbocation, okay? How would you do that? Typically, what we will do is we will have Rx, so like halogenal alkane. You add it with aluminium trichloride. It's the same idea as number 1 there. Instead of ClCl, I have RCl or RBr. So I'm just saying it's Rx there. Actually, let's make it RCl. Then you can see the similarity. Yeah? So same idea as above. You will get the Cl minus, forming dative bond to the empty orbital of aluminium, and then you will get an R+. This is your electrophile that your benzene can attack, yeah? The other one will be Friedel-Crafts acylation. Acylation is basically this. This is your electrophile. This is your electrophile for acylation. This is alkylation. All right. So it's the same idea, but we use acyl chloride. So obviously acyl chloride is much more reactive than halogen alkane, meaning reactive in a sense it's much easier to rip off the CCl because of the two electronegative atoms there. So you are just simply going to do similar chemistry. So as you can see, what is different in all of this is basically how you generate the electrophile. Once you generate the electrophile, I could just call them E+. Okay, and that's what I will do. The electrophiles are all electron deficient, electron deficient, electron deficient, electron deficient. Okay? So let's get started. So what do we know? I'll start off from benzene. Okay, I know I said earlier that we know that the delocalized structure is the most correct one based on physical data like enthalpy change of hydrogenation when you hydrogenate all the double bonds in a benzene ring. Okay, and also crystallographic data which shows that they are not alternating double and single because all the carbon bond length are actually equal. So there's a good sign that says that because all the carbon bond length are equal and they are actually longer than a double but shorter than a single, so they're somewhere in between. That's a result of the electrons getting delocalized around. Okay, I will show now how it will pick up an electrophile. I use an E+. Why? Because actually maybe I'll use one specific example. Maybe I'll use NO2+. Okay, the plus is on the nitrogen, but trust me, all those examples, if you know how to generate the electrophile, write the equation to show the electrophile being generated. It's the same mechanism. Okay, now the benzene is the one that's rich in electrons. When we talk about alkene, we talk about the pi electrons, right? In the benzene, you also have the delocalization of the electrons in the p orbital, which is unhybridized. Each of these is carbon sp2. Just like earlier, you have aluminium sp2, means you have an unhybridized 3p because aluminium is third period. Here you have an unhybridized 2p orbital on each of the carbon. Each of them is dumbbell shaped. They are orthogonal to the plane of the benzene, which is flat because it's trigonal planar. So these are orthogonal, meaning they are 90 degrees exactly to the plane itself. So the electrons in there, they can get delocalized, and that's what gives you the delocalization, right? Essentially, the electron density is richest above and below the plane. It's the double bond. The double bond is the one that results from the overlap of this orbital, sideway overlap of this orbital. So the rich in electron actually come from the double bond. Attacks the poor in electron density. Not from the carbon, from the double bond. Can you choose this double bond or this? Of course you can. I'm just showing this because this is the closest, all right? But the idea is from the double bond, the rich in electron, which is the pi electrons, localized, well, the one that get delocalized above and below the plane. You don't break any bond there. Well, actually, you do break something. You do break this double bond. This started out as a delocalized structure there. So that's why this is slow, because you are breaking. You are destroying the aromaticity. This is much, much, much slower compared to breaking a double bond like that of an alkene. When you do this, the alkene itself, yes, you break the double bond and you form carbocation. It's not as bad as this. This is really bad. That's why we need a really, really, really strong electrophile. And we need heat if we start from benzene, because we are destroying the aromaticity, something that it really likes. That's why it's slow. Okay, but regardless, it will proceed. I will get a bond formed between carbon and nitrogen, because that is the electrophile. The charge is on the nitrogen, so I take the nitrogen, not the charge. I have an original hydrogen there. I have an original hydrogen here. Just like when we did alkene chemistry, when we add the H here, I will get a plus charge here. When I add the H here, I'll get a plus charge here. When I add the NO2 plus here, I will get a plus charge here. All right. Then you say, are they the same if I add the NO2 to the other side? If I add the NO2 to the other side, I will get a plus charge there. Are they the same or are they different? Well, I tell you what, they are the same, because I hope you can see there is a plane of symmetry like that. So you can rotate 180 degree and you will get the exact same structure. All right. I hope you can see the symmetry there, so I don't have to worry about the other carbocation intermediate. It's important when you walk through this mechanism that you understand the changes in hybridization. This is a planar structure. All of the carbon are sp2 hybridized. All of them were 120 degree separated, yeah, as in the bond angles, okay? So what is happening here? So here is still double bond. In some books, because they started from the delocalized structure where they show like that, attacking the NO2 plus, what they will get to show this is, they will show as a half smiley face where the plus charge is like that, okay? I find that really confusing. I always do not like it. They are saying that the plus charge can get delocalized around, which is true actually, okay? But I've always found it easier if I look at it that way. This is the same as that. This is what I call the half smiley face, okay? But I always like this because I could relate it to the alkene chemistry, okay? Although I know I'm breaking aromaticity here, at the end of the reaction, I really want to get back my aromaticity because that is stabilizing, okay? So this second step is actually very fast because I want to get back my aromaticity, but I want to substitute this hydrogen with NO2 here. So I must kick out this H. I must return 2 electrons. I return the 2 electrons, not from the hydrogen, but from the covalent bond. The 2 electrons there go back to reform the double bond. Go back to reform the double bond. I would have lost electrons from that single bond there. So what does the H become? When it donates both electrons, this is heterolytic fission. The 2 electrons go there. That's why you get normal charge. This one will break. And what will you get? You will kick out H+, which has no electrons. It gave away the 2 electrons in the covalent bond to restore aromaticity. It is fast because you regain or you restore aromaticity. That means you re-get the benzene delocalization again. All right. So what is important here? I'll skip that structure because, you're more than welcome to use the half smiley face. I just find that by showing the cool structure, I could keep track of my positive charge easily and I could see what's going on. All right. So what happened to this H+, first of all? Okay. What happened to this H+? The H+ that is kick out, okay, after you finish the mechanism, what happened to it? Well, in each of these, like things like this, you have AlCl3 giving you the electrophile like that, right? So I know this is nitration. So nitration is that NO2. Well, guess what? I have a lot of H+, I have a lot of HSO4- lying around in my solution mixture. This has been used up. I have a H+, H+ will not react with this. H+ can react with this. So what happened is, the H+, because NO2 is produced from the corn nitric and corn sulfuric, so what I could do is I could react just with that, plus, well, cation reacts with anion, I will get that, and then regenerated. Strange, right? Because it uses the NO2, because there's the reactant from the nitric acid. The corn sulfuric acid is just acting as a catalyst in the reaction because you could get it back. When the H+ get kicked out in this reaction, it combined with the conjugate base to regenerate your acid. How about if I have a different reaction? Now, actually, before I talk about different reaction, let me just finish off this reaction first, yeah? So I'll put this in a different color because they are not the most important thing in the world, but they are important to understand regardless. I talk about carbocation intermediate here. You see a change of hybridization from carbon sp2 to carbon sp3, where you have 1, 2, 3, and 4. You have 4 sigma bond, which is 4 bonding pair of electrons on that carbon, and 0 lone pair, and therefore this is 109 degree, 109 degree, 109 degree, 109 degree, 109 degree. These are all carbon sp2 still. Even this is carbon sp2, it's a carbocation, right? Think about your electrophilic addition mechanism alkene. You will know this is carbon sp2, 120 degree, because 1, 2, 3 bond pair and 0 lone pair. Alright, so in terms of the energy profile diagram, you could have a reactant and a product. I'm assuming it's exothermic. The first step is going to be very, very slow. That is your activation energy for the first step. because you are breaking the aromaticity. You are restoring the aromaticity. It's going to be very fast because you are getting back the aromaticity. But regardless, there's still activation energy to be overcome for the reaction before they can react. Okay, so I'm assuming the enthalpy change is exo, but it really depends on the reaction, where they could ask you to do some calculation or they give you some information and then they ask you on the reaction profile diagram, which you need to label, of course, because a graph or diagram with no labels means nothing at all. What have I shown here? I've shown one mechanism where I have the benzene ring attacks the electrophiles. I get the carbocation intermediate, which I write down, and the second step is restoring the aromaticity by kicking out the H plus that I'm trying to replace with the electrophile. All right. Instead of NO2 plus, I'll show you another example. If I have let's say an acyl cation, so CH, well, maybe I'll just use the acyl cation above. So maybe this could be CH3 or CH3 CH2, then I'll get that, right? So I'll just generalize it by saying that it's R like that. So the rich in electron attack the carbon, which is poor in electron. So that is slow because I am breaking aromaticity. Now I could add it there. And then there's a H there. There's a H there. This is my carbocation because I added the electrophile there. If I add the electrophile there, my plus charge will be there, my electrophile will be there. But this is a symmetrical structure. You can draw the other one out, they will be exactly the same. Alright, so I will restore my aromaticity by breaking the CH. Oops, I've gotten this totally the other way around. I want that CH. I want to break that because I want this to be there. I need to kick out this one to restore the aromaticity. The two electrons from the covalent bond will reform the double bond and therefore complete the delocalization again. And then I will get this group substituted in an electrophilic substitution reaction. This is fast because it's restoring aromaticity. It kicks out the H plus, and the H plus can recombine with the AlCl4 minus to give you HCl plus AlCl3, which was the catalyst used, and you regenerate or you reform a catalyst because it is not used up in a reaction. Okay, so what have we shown here? I've just shown you that it's not that clear cut for this, but when you use a acyl cation, which is generated from AlCl3 plus that, or in the case of this, it's just AlCl3 plus the halogen alkane. This can also react with the H plus that comes off to regain back the catalyst itself. You also have similar property here. This can react with the H plus that come off from electrophilic substitution mechanism to give you HBr plus FeBr3 again. Same thing here. This could react with the H plus that's given off to give you HCl and the AlCl3 back again, because those are just Lewis acid catalysts. So I hope this electrophilic substitution mechanism makes sense to you. I've shown you with a cool structure because for me personally, I could keep track of the plus charge easily. You've seen some books where they show the delocalization, like half smiley face, as I mentioned before. That is perfectly correct as well. It's just that I find this better, and these are perfectly acceptable, provided you get the charge and the number of bonds correct, and you do all the mechanism correctly as I've shown here. They are perfectly acceptable by Cambridge International, and I don't think they'll be rejected by any UK examination body. So just because it's not shown in the books, if it is correct chemistry, there's no way you can be penalized. Alright, so that's it from me in this video. In another video, I'll cover specifically comparison between electrophilic addition of an alkene versus the electrophilic substitution of a benzene reaction. So in that upcoming video, you can see the difference exactly between the alkene chemistry and the benzene chemistry, how they are similar and how they are different. So this can constitute a part of an essay question, typically asked at an A2 level, meaning an A-level paper. Regardless, irrespective of whatever examination body you take, you should be capable of outlining similarity and differences between the mechanism now that you are more than well equipped with the basic knowledge. All right, I'll see you in the next video. If you like this video, if you like my teaching style, my explanation, please subscribe to the channel and share them with as many people as possible, your friends especially, who might be struggling as much as you, or who might do as well as you. So you never know. Okay, so I'll see you in the next video. Thank you for watching.